Okay, so with that knowledge, we are starting to discuss how to solve these conservation laws using finite volume. And the purpose of finite volume is to capture the behavior of the solution, not only in the smooth regions of the solution, but also for the shock waves. So that is very different from finite difference we have been working on for the first part of the semester. Finite difference aims to approximate the differential operators. And if you apply finite difference to Berger's equation, which we can, right, it'll solve the equation okay for the smooth regions before the shock wave appears. But who knows what is going to happen as the shock waves appear? We have a discontinuity. We no longer have spatial derivatives. And our approximation to the spatial derivatives, remember the approximation error is a function of the higher order derivative, right? We use Taylor series approximation, and the truncation error is like the higher derivative terms in the Taylor series. And the higher derivative terms in a discontinuous function is infinity. We get infinite approximation error if you use finite difference. It's just not a reliable method to use if you have anything discontinuous. The possibility of discontinuity in a nonlinear conservation law is what promotes us to switch to finite volume. And a happy coincidence, which we're not going to discuss in this lecture, but I think in the next lecture, is it turns out to be also better if you have non-uniform grids, or you have unstructured grids in multiple dimensions, where finite difference is still applicable, but it's a pain to construct finite difference operators for very complex mesh or non-uniform grids. But for finite volume, it's almost trivial to generalize a solution method from a uniform mesh to non-uniform mesh. So on this lecture, we are just going to discuss how finite volume solves a conservation law for uniform mesh, but when there is shock waves. All right. Okay. So if we want to deal with shock waves, we want to devise an approximation method for which form of the conservation law? Integral form, exactly. Because the other two forms are not useful anymore when you have a shock wave. So let's stick to the integral form when we think about trying to devise a finite volume discretization. And that's what finite volume means. The volume is a control volume, right? And we only have control volumes in the integral form of the differential equation. So let's start with the integral form. d dt of integral over L and R of u dx plus f of u, L and R is equal to 0. And the finite volume scheme specializes this by taking L and R's that are close to each other but not infinitesimally close. It's a finite volume. So let's say this is X, this is U, and we want to solve, let's say, a domain of 0 and 1. We divide the domain into n intervals, just like what we did in finite difference. But we are going to not focus on these grid points, but focus on these volumes. In finite difference, we focus on the value of the function at the grid points. In finite volume, we don't look at the value of the function at the grid points first. we first look at the integral of the function in between each two grid points. So this is delta x, 2 delta x, etc. Thank you. So we take L equal to I times delta x and R equal to I plus 1 times delta x. And the space between L and R, a volume of delta x, is the finite volume. And the ddt of that is equal to the value of the flux function u at left, which is I delta x, minus f of u at I delta x plus delta x. Okay, so this is a specialization of the integral form of the governing equation. This is still exact. There is no approximation to it. The approximation we need to make is to transform this exact form to a form we can solve using ODE45, using an ODE solver. Well, we want to approximate this function using a finite number of values. So this is a continuous function. We want to approximate using finite number of values. And if you remember the difference between finite difference and finite volume, and let's redo it in MATLAB. FD demo. So remember when we did finite difference, we draw an arbitrary function. Oops. We draw an arbitrary function. Alright. The finite difference scheme remembers the value of the function at the grid points. And anybody still remember when we use a finite volume scheme, what the computer remembers about the function?
The average of x.
The average. So let's redo that. We draw a function that is like wiggly. This is what the computer remembers, the average of the function within each control volume between I delta x and I plus 1 delta x. And why is it useful in this? How does the volume averages relate to this equation?
So the integration with the cell average.
This integration, this over here, is equal to the cell average times delta x. So this can be transformed, this can be represented as u bar of I times delta x. And now we see how we are transforming this into a differential, ordinary differential equation. If we can represent the right hand side, if we can not represent but approximate the right hand side using the cell averages, then we got a bunch of differential equations to solve. Alright, or if we can approximate this u at I delta x, which is on the left of this average, and also I plus 1 delta x, which is on the right of this average interval. Using all these average intervals, then we derive a bunch of ordinary differential equations. And the trick is unlike in finite difference, where we actually store these the value of the function at the grid points. In finite volume, we don't have the value of the solution at the grid points. We have to approximate them, or like in finite volume language, we want to reconstruct the solution u at the intervals. So we store the averages and we reconstruct the solution at the grid points. So we have U of reconstructed U approximation, let's say, as a function of U bar I minus 1 and U bar I, because these are the averages on the two sides of the of these points, minus F of U tilde UI bar and the UI plus 1 bar. So this is finite difference. Okay. And the U bar, the U tilde as a function of UI. So we usually say this. We should represent this as a U at I minus half, and this is UI plus half, because they are, if in finite difference, each I means a grid point. That is different in finite volume. Each I represents a volume. That means the grid points now becomes of secondary importance. That's why we denote them as fractional, like as half points, instead of as like integer points as in finite difference. That's because the volumes themselves are primary objects, and the interfaces or the grid points are of secondary importance. Okay, so U of I plus half as a function of U at I and UI plus 1 is the finite volume approximation. Okay. And after this approximation, this F is the numerical flux. We also call this F of I minus half, and this is F of I plus half. These are the numerical flux. The flux as a function of the reconstructed value at the grid points. Alright, any questions about this? And this is exactly the same for any finite volume schemes. The only difference between different finite volume schemes, you can be first order finite volume, second order, you can be higher order finite volume. The only difference is how do you approximate U tilde as a function of UI and UI plus 1, or how do you reconstruct the interface solution. Also, there are some other finite volume schemes that tries to directly reconstruct the flux at the boundaries instead of trying to reconstruct the solution first and then computing the flux. Alright. So finite volume schemes, basically you need to reconstruct the flux at the boundary as a function of the averages of the solution.